Hello, and today we're going to be looking at complex numbers. In particular, I want to actually define what a complex number is, and then we'll go into some more uh, theoretical things. So, what is a complex number? Well, a complex number can be defined as a set, like most numbers, in this form. So this x plus yi such that x and y are elements of the real number set, and I equals the square root of -1. So here we have defined a set for a complex number. So is 0 a complex number? Yes, it is. You can have 0x and 0y. That's still 0, so 0 is technically a complex number. Pi is also a complex number, if you think about it. You can have 0y and pi x's, and it will still work. You could also say that just I by itself is an imaginary number. You can have 0x and 1y, and bang, you have I. You can also have combinations of things like 2 plus 2i, where x and y are both 2. So all of these are complex numbers. So with that in mind, let's do some addition and subtraction of complex numbers. Now, complex numbers are generally written as a z. So I'm going to say that z1 is going to equal 2 plus 2i, and I'm going to find z2 to equal 3 plus 7i. So now I want to add z1 to z2, z1 plus z2. So what does that equal? So all we have to do is think of I as just another pronumeral. So forget about its ability to be the imaginary number. Just think of it as just another letter, and you're just collecting like terms. So you have 3 plus 2 plus 2 plus 7 I, if you really want to think of it like that. So we get 5 plus 9i is equal to z1 plus z2. Similarly, if we want to go do some subtraction, we're just collecting like terms again, but this time we're making it slightly negative. So z1 minus z2, well, z1 is 2, and 2 minus 3 plus 2 minus 7 I. And then we can say that this is just -1, and this is -5i, and that's our subtraction. So you can see that that addition and subtraction is just collecting like terms, and you don't have to think about it too much. So now that we've done addition and subtraction, let's do some multiplication and division. So again, with our z1 and z2, I'm going to now multiply these two together. So z1, 2 plus 2i, lots of 3 plus 7i, and we can just treat this as a quadratic and just expand. So we can use our FOIL first. So 2 times 3 is 6. Outer 2 times 7i is just 14i. Inner 2i times 3i is just 6i. And last 2i times 7i is going to be 14i squared. So now we can collect like terms, and we can also recognize that this 14i squared here, let me just highlight that. This 14i squared is going to simplify down to -14. So now we have 20i minus 14 plus 6, and then we can collect like terms again, and we get 20i minus 8. So now what about division? Well, division, we're going to do something different. Rather than timesing together, we're going to divide, but there's one key difference between division and multiplication. Rather than just leaving it as a fraction like so, we're going to actually have to get rid of the I on the bottom there. So we can't have an I on the denominator, because if we wanted to find the coefficient of I, or if we wanted to solve for x and y, referring back to the definition of the complex number, we can't do it if it's in this fraction form. So what we do is we use the conjugate. So the conjugate of 3 plus 7i is going to be 3 minus 7i, and then 3 minus 7i, and now this is just 1, so this doesn't affect. I have a video all about conjugates. In that video I call it complements, but that's not right, it's a conjugate. So now that we have the conjugate, we can just times these. So now 3 plus 7i, we can just times these together. It's going to become 9 plus 7 squared, 49. I will prove why that is correct in just a moment. But now let's focus on the top. So we can use FOIL again. So 2 times 3, 6. And we've done this before, but now we're gonna have the negative 7i. So first outer 2 times negative 14i, inner, that's just 6i, then last 2i times 7i is going to be 14i squared. This will cancel out and it will become positive 14. This here we can simplify down to 58. So now coming up here, 58 over 6 plus 14, that's 20, minus 20i. So now that we have this fraction, we can work out what x and y is. And sometimes you would see in textbooks that they like to split it like this, so it becomes 20 over 58 plus or minus, in this case, 20i over 58. You will sometimes see that they put the I over here, but that's how I normally leave it. So now let's look at why this expression here, when times together, is going to give me two positive numbers. So if we think of x plus yi and x minus yi, and if we were asked to expand this, well, we can do it using FOIL. So it's going to become x squared, first outer, x times, it's going to be xyi, then inner yi, xyi, and then last, it's going to be minus y squared I squared. These two cancel. This I squared becomes negative 1, so this becomes a positive. So we're left with x squared plus y squared. It's the same reason why we could simplify down x squared plus 9 into x minus 3i times x plus 3i. So now let's look at higher powers of I. So I by itself is just going to be root negative 1, or just I. I squared is going to be just negative 1 based on the root here. So what's I cubed? Well, I cubed is going to be I squared times I again. And that will give us negative I. What about I to the 4? Well, that can be I squared times I squared. And that is just negative 1 times negative 1, which gives us 1. And what about I to the 5? Well, it's going to be I to the 4, 1 times I, and we're going to get I. So what we're going to have is this infinitely repeating pattern of I minus 1 minus I, 1, I. And this will repeat infinitely. So, does this work for negative indices? Well, of course it does. I to the negative 1 is just going to equal 1 over I. We don't like I on the bottom, so we're going to times it by the conjugate. So what we get is I on the top over I squared. I squared is just negative 1, so we get negative I. And we can keep doing a similar pattern for all negative indices. So what if we were asked to solve for I to the power of 33? Well, we can look at this and realize that I to the 32 is a multiple of 4. And times I, and that will give us 33. This I to the 32 is just I to the power of 4 to the power of 8 times I. I to the power of 4 is 1. 1 to the power of 8 is just 1 times I. We get I to the 33 equals I. Okay, so the next bit that I want to talk about is the conjugate of Z. So if I had Z is equal to x plus y I, and I wanted the conjugate, what's going to change? It's just going to be the y value. So it's going to become x minus yi. Now these two expressions aren't equal, but we have a special notation for the conjugate of a complex number. We put a line on top of the z. So if we were given this z value here, and we saw the z with a line on top, and we were asked to solve, it's just asking for this bit. It's just asking for the conjugate. So now let's look at some notation quickly of z. So if z is equal to x plus yi, we have two functions that we can apply to z. One is the real and one is the imaginary part of z. And we can use this later on to graph, but the real part of z is always referring to x, and the imaginary part of z is always referring to y. So the real part is of course referring to any number on the actual number line, and the imaginary part is looking at the part that's imaginary, in this case yi, but we're looking at how many I rather than the entire term. So that's all the time that I have for today on complex numbers. If you have any questions, feel free to leave a comment in the comment section below or contact me on social media, and I will see you in the next video.